All right. So if you were gone yesterday, I had a force plate out. I stood on it, and when I'm just standing on the force plate, it reads 1050. Okay, might read a little less. I ate pretty well yesterday. That's a lie. I had John's for dinner in a week moment. 1050 newtons FG, 1050 newtons smoosh push scale. I'm just standing still. Okay, and then we talked about what happens if I crouch down and then jump up. And this was the graph that we got from the force plate reading versus time. So this is the smoosh push interaction with the force plate versus time. Before I leave the ground, it kind of spikes here because when I'm crouched and I'm pushing off here, I'm accelerating my belly button upwards. That requires an unbalanced force in the upward direction. Okay. At B, we identified that unbalanced force is about 2,000 newtons. You look over and you can see that on the scale. So the free body diagram for me at B shows that 1050 down gravitationally, that 2,000 up smoosh pushally, unbalanced force in the upward direction. Okay. The other free body diagram that we drew up above, from C to D, you see zero reading on the scale because I'm not touching it. I'm not interacting with it. If I'm not interacting with it, I'm not experiencing a smoosh push from it. So it's just my gravitational force while I'm in the air. The unbalanced force is 1050 newtons down, and 1050 newtons over 105 kilograms, 10 newtons per kilogram. In other words, my acceleration while I'm going up and coming back down is negative 10 meters per second squared. So then we went through and we did some calculations, and for the impulse that I guess I should explain further. The unbalanced force that I experience here at B, I don't want to use that to figure out my acceleration when I'm pushing off on the ground, because that's a spike. Okay, it's not that much force the whole time. Over here, it's clearly less than that. So that's why we're going to use this impulse change of momentum idea. The area bounded by this graph has the unit Newton seconds. And we approximated this as a purple rectangle and a yellow triangle. And then the area of the purple rectangle is 1,000 newtons tall by 0.44 seconds wide. It goes from 4 to 4.44. The triangle has a height of 1,000 newtons. As it goes from 1,000 up to 2,000. It's got a base of 0.44. So I add those two areas together. I got about 660 newton seconds. That's the impulse from the smoosh push. So if I set that equal to my mass times my change in velocity, I get that in pushing off, my velocity went from 0 to 6.3. And I think you did a more exact calculation because I see that number 6.5 here. So I leave the ground going 6.5 meters per second, and I am immediately slowing down at this acceleration of negative 10. That would make the time here 0.65. And the area then was about 2 meters, right? So that's saying I jumped 2 meters off the ground when I do this. Okay, but you're looking at it, and quite clearly I'm not jumping 2 meters. So what's the issue here? And I don't know that we got around to chatting about that, but maybe we did. We didn't. Okay. We started to. We were just about to. Seems like I'm not going that fast. Okay. So what issue am I running into here? Sorry, you're going to have to come back to this from yesterday. Okay. So have a quick chat with your neighbor. What's going on here? And I will tell you this, our kinematics is correct down here. Okay? If I leave the ground at 6.5 meters per second, I would be in the air, it would take 0.65 seconds to get to my highest point, and that would be 2 meters off the ground. Okay? It's not there. It has to do with what's going on up here. I'm not getting an impulse of 660 Newton seconds. Or I should say my change in momentum is not 660 Newton seconds. And so this kind of comes down to important understandings about the way that equation is set up. Any insights here anybody has to offer at the Mo? Ronan, what are you thinking?
The change in velocity, is that like from like the minimum to the maximum?
Yeah, that like according to this calculation, a 660 Newton second change in momentum would change my velocity from 0 to 6.3. But I'm saying that this is an overestimate of the change of momentum that I acquired. Okay? What do you got?
Yeah, because the formula is so because you were timing 1,000 to the time, like the force to the time. Is that fine? Can you find with that equation the momentum? Because isn't it like at a VP like at find the velocity times mass minus initial velocity times mass, like you're timing the force to get the momentum.
So you're talking about like if I have MVF minus MVI, what's the other side of that equation look like? I. Okay, Pedro offers FU delta T. Because this comes from whoa, buddy. This comes from FU ma. And saying that M is just delta V over delta T. Or sorry, that A is just delta V over delta T. So that's where this equation comes from. Now, I'm compensating for the fact that the force is not constant by using the area. That's why we're doing this whole impulse thing. But if you look at this equation, what it's saying there, why am I not getting a change of momentum equal to the area under that graph? Well, it kind of comes back to this diagram here. How would you get my unbalanced force here? In a sense, okay, I'm going to do a force addition diagram of these two arrows, and it's not going to be 2,000, right? It's going to be like 1,000 down and 2,000 up. Because there's not just this smoosh poosh, there's also this gravitational force. So I'm not experiencing one force, I'm experiencing two forces. This graph is only looking at one of those forces. In addition to that upward smoosh poosh force, I'm also experiencing a downward gravitational force. And if I were to graph that, that's going to be kind of going along like this. So in this little window of time here, where I had that yellow and purple, I also had this green deal below the axis. So if we're talking about impulses due to forces, green is the impulse due to the gravitational force. Purple and yellow are the impulse due to the smoosh poosh. If change in momentum is dependent upon the unbalanced force, what area do I want to look at here? Run that by your neighbor real quick. So purple and yellow, that's the smoosh poosh impulse. Green, that's the gravitational force impulse. What's going to give me my change in momentum here? Ronan, what are you thinking? Strictly yellow, just that triangle. Because this green rectangle, if I can move it, and I can't, but if I could, that green rectangle cancels out the purple rectangle. So all I'm really getting for an impulse is just the bit from this yellow triangle here. Okay, so that's this bit. Half of 1,000 times 0.44. So 1,000 times 0.22. So that's 220 Newton second. Aye. That's not how math works, Mr. Harding. 220 Newton seconds. And if I take 220 Newton seconds divided by my 105 kilogram mass, what am I going to get for my change in velocity? Somewhere in the ballpark of 2. So I get that to be 2.1 meters per second. That's my change in velocity. Okay. This is the impulse divided by the mass to get the change in velocity. So if I run with that, my velocity versus time graph doesn't go all the way up to 6.5. This is just 2.1. The nice thing about a slope of -10, you can already see it over here. If the velocity here was 6.5, it takes 0.65 to go to 0. So if the velocity over here is 2.1, it's going to take 0.21 to go to 0. This area is how high I jump. Half of 0.21 seconds times 2.1 meters per second. What's that going to shake out to be? About 22 centimeters. So when I'm jumping, I'm jumping about that much off the table, about 22 centimeters. Okay. Koba, would that give me on varsity here? Volleyball? Probably not. Okay. You need bigger ups than that. That's about 8 inches. Okay. The greatest leaper of all time in NBA history, at least so long as I was paying attention to it, was Spud Webb. And let's see, Spud Webb's height, 5'7". Who's 5'7" in here? Somebody. Quacky, you 5'7"? 5'4", okay. Emma, you 5'7"? 5'5"? Nobody's 5'7"? 5'8", okay, stand up. So Spud Webb in heels. Okay, that's that. Can you dunk? You cannot dunk. Okay. Spud Webb can dunk. So let's watch this here.
And Dave Cowens, the former Celtic great.
5'7".
Now, Spud's first attempt.
He was 8 years old at
In
the
the
time.
dunk competition, and John looks like he's measuring things out.
Not really, it just looks like it.
Well, he is. He's got a flair for the dramatic, Rick, and he's a hometown guy. The crowd really loves him, and he's fresh off his visit on the Tonight Show.
Come on,
the other
Spud
night,
Webb, go
so,
dunk it.
He's got a flair.
Oh, man, you can't even
John,
dunk.
looked
That
like it
bounced
hit
out.
Spud and came out. That's
Come
what
on,
I'm saying.
Spud
I
Webb.
hit him in the head, I think, and bounced back out of the basket. It looked like he
That doesn't
didn't
count.
make the shot, though. Well, we're going to have to get an official ruling from Norm Drucker. You see him saying that the ball hit me. Yes, he
Oh, he's
hit
saying
the
it hit him on the
basket. That's
head.
what he's claiming. This is Norm checking out. They're giving him the
So
ball.
then they
Looks like
review
he's
it.
going to have to take, also just verifying it.
Let's
take
see
a
here.
replay. There it is.
Yep, it goes down, bounces off of his
Oh,
head.
boy, it's right now.
I don't have those problems when I play basketball.
5'7". The littlest man in the competition.
This is like the extended edit. It was a lot quicker last time around. Sorry.
Spud Webb gets that move. There's the two-hand plant, the footed plant, the double clutch. He takes it home. Not only does he get up there, but he hangs, Rick. You know, I'm picking up some. Looks like he's taking a shot.
Here we go.
Now, the timing that ball is bounced just right. He meets it at the height and does the reverse.
So this is what it looks like in Jonah's dreams. All right. 43 centimeters? 43 inches. 43 inches. So it's about there. So that's what it would take to get Jonah. All right. Cool. The other stuff I had for you here today before I get you on to the mastering time is some review items over on a Pear Deck. And this is a scale one. Let me get you a fresh one here quick. And the items themselves are in Canvas. So if you want to pull up today's Canvas page, there's a selection of some conceptual questions. And the first one is this. There's a 10 kilogram box initially at rest. It's moving along a frictionless horizontal surface. A horizontal force to the right is applied to the box. The magnitude of that force changes as a function of time, as shown here. So this is a little different than what we were just talking about with my jumping. When I was jumping, there was gravitation in opposition to smooch boost. Here, there's no friction opposing this force. Okay? So a student's going to calculate the impulse applied by this force. During the first 2 seconds, they get 4 Newton seconds, and the impulse applied during the following few seconds, they get to be 6 Newton seconds. So over on the Pear Deck, what, if anything, is wrong with those calculations? And if something is wrong, what is it? How should they correct it? If it's correct, explain why that it's correct. And it is a Pear Deck of NNGPD. There you go. You can take it to be unbalanced force. There's nothing opposing it. got first 2 seconds is 2, but I think let's see. During the first 2 seconds, the pulse should be 2 Newton seconds, not 4 Newton seconds. The area of the triangle is 1/2 base times height. So height 40 centimeters divided by 2. Oh, this is gross. Area of the first 2 seconds should be a triangle. That area of the triangle should be divided by 2. So there you go. So important understandings and graph skills. It's a graph of force versus time. So the area is Newton seconds, and pay attention to the shapes. That first shape is a triangle. So yeah, that should be 2 Newton seconds. And then the next 3 seconds is a rectangle that's 2 Newton seconds tall. So it's 2 Newtons tall. So 6 Newton seconds is correct there. All right. Again, if this is tough to read, you can pop on over to Canvas. It's living over there. Let me hide this thing. You got a same graph, okay, but now the output instead is a graph of momentum versus time. Okay. So how many of you have encountered a graph of momentum versus time before? Right? That's kind of a weird one. This is a common thing for them to do to you on the AP exam, like some kind of a weird graph that you're not used to. So my advice to you is to look at the features that we find most important on graphs, which are what, typically? Point schmoids. Seems like we talk about slopes on graph a lot. What else? Area between the graph and the x-axis. So do a little dimensional analysis. If this is kilogram meters per second this way, and this is seconds this way, what are the units of the slope? What are the units of the area? And see if that helps you quickly decide where the errors or issues are. But this is the given item. We're given this. The student produced the momentum graph. So what errors do they have there? So from a friend, we have this. Slope units are kilogram meters per second squared. Area units are kilogram meters. What's a kilogram meter per second squared? That's newtons. Okay, so that's important to know. So the slope of that graph is newtons. The slope of the momentum graph is newtons. The area are kilogram meters. What the heck's a kilogram meter? I don't know. Okay, sometimes the units are gibberish. So that's not important here. The slope is. So think about how the slope of this momentum versus time graph should look if it's a plot of force versus time that we're going with up above. All right. All right. So like what I'm reading back here, I think we're flipping it around. The thing that's correct is the upper graph. That's the graph they're given. They're given this plot of force versus time. And then they're supposed to create a momentum time graph from it. So if you look at this thing, during the first 2 seconds, if I calculate the slope, this goes up 2 kilogram meters per second squared. It goes over 2 seconds. So that would shake out to be 1 kilogram meter per second squared, aka 1 Newton. What's the problem with that based on the upper graph? Is it 2 the whole time? No. So this is acting like the upper graph is this. It'd be correct if we had a constant 1 Newton the whole time. We don't have a constant 1 Newton the whole time. What's happening to the force here? Yeah. So now you got to employ your position versus time graph and velocity time graph skills. Okay. So it's kind of like this is the position versus time graph, and your velocity versus time graph is a straight diagonal line. Okay. That would be a position versus time graph that is parabolic and eventually gets to that slope. Okay? Because it starts off with a force of 0. That means this has to start off with a slope of 0. At some point, the slope would be 1. Eventually, it has to get to 2. And you run into the same problem down here. From 5 to 8 seconds, this starts out with a force of 2, but by the end of that, the force is 0. And then for this last bit, the force is 0. So that's why this is correct. This has got a slope of 0. But we're going to have to slowly taper to that value. So this also needs to be parabolic. Okay? And because you have a changing force, you should have a changing slope. It's decreasing 0. That's what's happening in this way. So it's the same slope skills that we do with velocity and position graphs, but they're just in a different framework. All right. Ranking task. So you've got 8 cars moving along horizontal roads, and the speeds are given to you. You're also given the mass of the cars. The cars are the same size and shape, but they carry different loads with different masses. All the cars are going to be stopped by plowing into identical barriers. All the cars are going to be stopped by the same constant force from that barrier. So rank these situations from greatest to least on the basis of the time that they're going to need to stop. Put first the car that requires the most time to stop. Put last the car that's going to require the shortest time to stop. Okay? So I'll shut up and leave you to that. Oh man, have we done ranking tasks before? So go with like A greater than B equal to C type of motif. Greater than and equal signs. Bunch of savages. Couple different options back here. I got somebody with H equal to G greater than F, greater than B equal to C greater than equal to D greater than A, and somebody else with C greater than D greater than A equal to F greater than E greater than D. So run that by your neighbor real quick. You got any thoughts on that?
So at this point, how about because what I did is to reply that's why more or less.
Okay, right.
And all of what's right. Just so you want to hire them. You have to hire. So it's all I like this.
Oh, yeah, I haven't done that work. It's where you have to, yeah, I don't know.
Alright, now it's looking like a whole lot more. G equal to H greater than F, C equal to D, B equal to E. So is it B equal to E or F equal to E? B equal to E, B equal to E. F equal to E. And you put it in the alphabet. Okay, so what we're looking at again here, you've got enough information to figure out the change in momentum, and the change in momentum has to equal the impulse. So for this one, it starts out going 20, it's 3,000 kilograms. It's going to end up stopped in the end. They all end up with a final momentum of 0. So 0 minus 60,000, 0 minus 60,000, 0 minus 40,000, 0 minus 20,000, 0 minus 30,000, 0 minus 30,000, 0 minus 20,000, 0 minus 10,000. Those will be all the changes in momentum. those would be all the impulses. They're all going to be stopped by the same force, so it's going to take more time to stop the one with the bigger impulse. So that's how H and G end up up front. That's how A ends up least. That's how B and E end up equal. And C and D end up equal. And F is going to be 40,000. So that's why it's G equals H then F. All right. Okay, let's call that good. I wanted to talk about one other thing quick before I give you like only 2 minutes to work on mastering, but hey, you got to ask. And that's the survey that I threw at you the other day. So I actually threw three surveys at you, but you only got one of them, okay? And I kind of targeted them based on test performance. So I was trying to see if there's any kind of patterns to that, but I was kind of like sweet about it. So I just went through the grade book and took like the top third of test scores, and they got this survey. Middle third got another survey, and then a bottom third got an additional survey. It's all the same survey, but I was just looking for patterns and answers, just because that seemed kind of sciencey, right? Try to find a rhyme or a reason. What are the students that are successful on the test doing? So top 30 scores. At any time prior to the exam, did you find time to either email me a direct question about the mastering or stop by outside of class time to deal with it? Of that 18, so 6, none of them, they didn't do it at all. So 6 of the 18 didn't even stop by or ask questions at all. 6 of the 18 did it once. 6 of the 18 did it several times. So just kind of know that, okay? They're being successful on the test, but they're still needing clarification on mastering stuff, and they're finding time to make that happen. So I would encourage all of you to make that happen. Again, that kind of varied a little bit group to group to group. Drawing velocity versus time graphs when dealing with motion problems. Oh, let me get the cursor over that. Is that 2 people or 3 people? 2 people do it rarely. But 16 of the 18 do that half of the time or more. They're drawing a velocity versus time graph when they're dealing with a motion problem. That was a little less common for the middle third of test scores. Solving it with just the equations. So I've got a motion problem. I'm not drawing anything at all. I'm just solving it with the equations. That's rarely for 8 of this 18 that they would do that. 1 of the 18 would never just solve it with the equations in this top third of scores. There is one person in that 18 that does that all the time, but that's rare, okay? So I want to point that out, that this process of using the graphs to solve the problems, it's used by the students that are in that top third of scores, okay? It'll get the job done. Unbalanced force problem, solving that with just the equations. Again, 2 would never just solve it with the equations. 10 would rarely do it that way. You got 3 that are doing it that way all the time. So just setting it up, maybe working through it in their head, and then just doing the calculations, finding the answers that way. But that's kind of a rare thing. So again, I wanted to kind of emphasize that, because for the middle third of test scores, they were more commonly indicating that they were trying to solve motion problems just with equations, or trying to solve the unbalanced force problems just with equations. It was more than half of the middle third of tests that said that. And you can see that's kind of a rare thing, or a rarer thing, in the top tier of test scores. System schemas, that was pretty rare everywhere. And that showed up on the test. Drawing free body diagrams. You can see for 9 of the, or actually it's probably 10 of the 18, they draw free body diagrams all the time when they're doing force problems. Whatever that would leave us, 7 or so are doing it most of the time, and you got 1 that's doing it half the time. So all of them are doing it at least half the time, drawing a free body diagram with a force problem. And then the force addition diagram. And again, you got a couple, 2 here of the 18 that are rarely drawing the force addition diagram, but 5 of the 18 draw it most of the time, and 11 of the 18 are drawing it all the time, okay? And I saw that a lot when I was going around. We did the elevator problem here, right? This thing the other day. Okay. So when I was going around in different periods, that was probably the biggest hurdle to getting this done well. Drawing the force addition diagram. Really, a system schema is pretty important there as well to try to identify the correct number and types of forces that you should have. Flavor of the force. I guess the other thing I wanted to mention, the FBDs and CATs, or yeah, you call it a CAT here. So the FBD and CAT, really common in this top third, less so for the lowest third of test scores. So the lowest third of test scores, it was right about half of them are drawing free body diagrams when they're doing force problems, and about half of them are drawing the force addition diagrams. Okay? Which is not to say that just by drawing the free body diagram, you're going to instantly end up in the top third of test scores. But it's a common strategy that's used by those students. So if you're not doing that, I would certainly encourage you to do it. And if you are doing it but not being successful with it, that's certainly something to come in and visit with me about and see if we can get you a little more successful. Okay? So that's the that of the survey. Let me get your tests back at you so you can see how I did that. Context for that. Where's those tests?
I guess you would know too. Was it group set to be able to yeah, for the this adds the yeah. Yeah. The way that it was working, yeah. The way it was working is you have the first and second roll twice. And I was like, oh man. Yeah. It was like instead of saying the value of the sum of the take the number of points based on your die plus the number. Like, you see.
Cover. Pedro. Emily. Glenn. Clayton. Grace. Sean. I had it.